Number of positive integers less than 50 having exactly two distinct factors other than 1 and itself, two distinct factors or 4 factors totally, or number n should be of the form p into q, or it should be of the form p cube. P into q, where p and q are distinct primes. The factors are 1, p, q, pq. This is 1, this is n, two other factors. Number of the form p cube, 1, p square, p cube. This is 1, this is a number itself. Other than 1 and itself, two other factors. 4 factors totally. Other than 1 and itself, 2 factors. So what are the numbers we're looking for? P and q should be distinct. So I'm thinking about 2 into 3, 2 into 5, 2 into 7, 2 into 11, 2 into 13, 2 into 17, 2 into 19, 2 into 23, 2 into 29 will go beyond. All of these are possible. So 1, 2, 3, 4, 5, 6, 7, 8 numbers. Then what do? We say 3 into 5, 3 into 7, 3 into 11, 3 into 13. Another 4 numbers here, 8 numbers here. 3 into 17 is 51. I don't have to worry about it. After this, we have 5 into 7, 35, and 5 into 11 will become more. One number here. I don't have to worry about 7 into 11, so that's way above 50. So 6, 10, 14, 22, all of these numbers, 8 of them, plus 4, 12, plus 1, 13. I almost marked down 13 because I'd completely forgotten this. P cube could be 2 cube, could be 3 cube. This is 8, this is 27. 5 cube is 125, I don't have to worry about it. So these 13 numbers plus those 2 numbers, 15 numbers totally, will have a total of 4 factors or 2 factors apart from, 2 distinct factors apart from 1 in itself. Totally 15 numbers. The number of integer solutions of the equation x square minus 10 whole part x square minus 3x minus 10 equal to 1 is a very beautiful question. First of all, something power 0 is 1. 1 power anything is 1. So what do we now need to do? We have to solve for this going to 1 or this going to 0. Get those values, substitute in the other part, and then see if it is logical, whether it does make sense. And so what I'm going to do, I'm going to solve 2 different equations. I'm going to say x square minus 3x minus 10 equal to 0. Get the answers. I'm going to find x square minus 10 equal to 1 and get the answers, and then think about simplifying this. Nice. So x square minus 3x minus 10 is 0, or x minus 5 into x plus 2 equal to 0. X is 5 or x is minus 2. If there are 5 square minus 10 whole power 0, that will be 1. If there are minus 2 square is 4 minus 10, minus 6 power 0, that is 1. So 5 works, minus 2 works. Nice, brilliant. 1 power anything is 1. That is super interesting. So we'll say x square minus 10 is 1, x square is 11, x is plus or minus root 11. The 2 possible values, this could be root 11, in which case that will be some irrational thing. Do we need to worry about it? I don't need to worry about it at all, because in this case, we talk about integer solutions. X equal to plus root 11 minus root 11 simply doesn't work. If something per something is 1, either this base should be 1 or that number there should be 0. Put base equal to 1, solve. The exponent should be 0, solve, we are through. Have I completed everything? No, I have not. There's one more possibility here, which is minus 1 square is 1, minus 1 power 4 is 1, minus 1 power an even number is 1. So there is a possibility of that happening, in which case I'll have to verify that. So I'm going to solve for x square minus 10 equal to minus 1, or x square equal to plus 10 minus 1, which is 9. That means x is equal to plus or minus 3. I got this far, but I cannot be sure that this will work, because for plus 3 and minus 3, my exponent should be an integer. More than that, it should be an even number. If it's an even number, then I am happy. But minus 1 power 101 will be minus 1. Minus 1 par 94 will be plus 1. So to substitute x equal to plus 3 minus 3, I have to verify whether it turns out to be an even number. Let's do that. This is x minus 5 into x plus 2. I put 3 minus 5 into 3 plus 2, which is minus 2 into 5, which is minus 10. Yeah, that works. I put minus 3 minus 5 into minus 3 plus 2, minus 8 into minus 1 equal to 8. This also works. Both are even numbers, both work. Therefore, x could be 3 or minus 3. We already got that x could be 5 or minus 2. So we have 5, minus 2, 3, minus 3. For 3 and minus 3, this goes to minus 1. That's an even number. We are very happy. For 5 and minus 2, this goes to some number that goes to 0. We are happy. 4 different values are possible. Beautiful question. The number of distinct integer values of n satisfying this is. And so this by this should be less than 0. Right? That means we could have a scenario where it is positive by negative or negative by positive. Nice. So what am I going to do? I'm going to think about when does this become positive and negative? When does this become positive and negative? I'm going to solve for 4 minus log n to the base 2 greater than 0. Okay. Or log n to the base 2 is less than 4. 2 power 4 is 16, n less than 16. N is less than 16, this is positive. N is equal to 16, this is 0. N greater than 16, this is negative. Same funda, this one. 3 minus log n to the base 4 greater than 0. Log n to the base 4 is less than 3. N less than 4 cube, 64. And so, if n is less than 16, this is positive. If n is less than 64, this is positive. So, I'm going to break our world into 3 parts. Less than 16, 16 to 64, greater than 64. Nice. Less than 16, this is positive by positive. Greater than 64 will be negative by negative. This is negative, this is definitely negative. What happens at 16? At 16, this goes to 0. What happens at 64? At 64, this goes to infinity or undefined. So, it is less than 0. So, I'm worrying about 16 to 64. In this case, the denominator is positive, numerator is negative. This is the range we are looking for. 64 to 16, but without counting 16, without counting 64. Or 17, 18, 19, 20, 21, all the way till 63. The first 63 natural numbers, subtract the first 16, 47. 17 to 63, all the numbers included. 17, 18, 19, 20, 21, all the way till 63. Break it down to the 3 regions. Think about negative by positive, positive by negative. Here it is both positive, here it is both negative. In between it works for us. That's the first step. Then be careful about, hey, am I counting 16? Am I counting 64? Is it less than 0 or less than or equal to 0? I'll be a little careful with doing the math. Then you're through. All numbers from 16 to 64 or between 16 and 64 without counting 16, without counting 64. All integer values. The number of integers greater than 2000 that can be formed with the digit 0, 1, 2, 3, 4, 5 using each digit at most once. At most once. That means no repetition. So maximum we can form 1, 2, 3, 4, 5, 6 digit numbers. Using these 6 digits, we want to find all integers greater than 2000. 2000 as a 4-digit number. We are basically counting all 5-digit numbers, all 6-digit numbers, and then some 4-digit numbers. I'm going to think about 5 digits. Then we'll think about 6 digits. Then we'll move on to 4 digits. 1, 2, 3, 4, 5. This digit can be 1, 2, 3, 4, 5. This cannot be 0. The starting digit cannot be 0. Right? Let's say this is A. This one, it can be 0, but it cannot be A. Why? Because each digit is used at most once. It cannot repeat. call this B. This digit 0 to 5 except A and B. Or there are 5 options for this. Out of 6 we subtract A, 5 options for this. Out of 6 we subtract A and B, 4 options for this. Here what will we do? We'll say 0 to 5 minus of A, B and C. Out of 6 options we subtract 3. 5 into 5 into 4 into 3 into 2. Not many 5-digit numbers are possible. Let's move to 6-digit numbers. A, B, C, D, E, F. Nice. A has again 5 options. 1, 2, 3, 4, 5. B would be 0 to 5 minus A. 5 options. 0 to 5 minus A and B, 4 options. 3 options. 2 options. 1 option. It will be 5 into 5 into 4 into 3 into 2 into 1. This is 5 into 5 into 4 into 3 into 2. Both are same. There's an additional 1 there. That's it. 5 into 5, 25, 25 into 4, 100, 100 into 6, 600. 5 into 5, 25 into 4, 100 into 6, 600. 600 5-digit numbers, 600 6-digit numbers. Now let's move to 4-digit numbers. Looking at 4-digit numbers, more than 2000. The first digit cannot be 1. It can only be 2, 3, 4, 5. Very interestingly, if the first digit were 2, all possible numbers are more than 2000. So you don't have to worry about first digit being 2 and not counting a few numbers. All numbers with first digit 2 will count. Right? So A, there are 4 options. B, 0 to 5 except A, 5 options. 4 options here, 5 options here. C will be 0 to 5 minus A comma B. 3 options here. 4 into 5 into 4 into 3. 4 into 5, 20. 20 into 4, 80. 80 into 3, 240. So we had 5-digit numbers and 6-digit numbers, 600 and 600 each. 4-digit number, 240. 1200, 1400, 1440. Hopefully that's there in our choices. Yes, it is. Done. The number of integers n that satisfy the inequalities, modulus of n minus 60 less than modulus of n minus 100 less than modulus of n minus 20 is very interesting. First thing we need to know is if you have 2 points on the number line, x and y, then the distance between these 2 points is modulus of x minus y or modulus of y minus x, one of the two, doesn't matter. Right? So now we're going to treat this as this inequality and then this inequality. Then so let's say modulus of n minus 60 less than modulus of n minus 100. So let's put 60 here and 100 here. So distance modulus of n minus 60 less than modulus of n minus 100. That is, if I have n, distance from 60 is less than distance from 100. Right? Or think about this, if n were here, distance from 60 would be less than distance from 100. If n were here, 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 throughout it will work. There will be the turning point will be at 80. Modulus of 80 minus 60 is equal to modulus of 80 minus 100. So where will it work? Where will it hold good? It will hold good when n is less than 80. N can be anywhere here. Modulus of n minus 60 will be less than modulus of n minus 100. Because 40 minus 60 modulus is 20, 40 minus 100 modulus is 60. So this tells us n is less than 80. Let's attack this one. So for this, we're thinking about 100 and 20. We know straight away that the turning point is 60. Distance from 100 is less than distance from 20. Or this number is closer to 100. Or n should be greater than 60. This one works when n is less than 80. That one works when n is greater than 60. We're looking for numbers greater than 60, less than 80. 61 to 79. 19 different numbers. That's an answer. 61, 62, 63, 64 till 69. Clearly we are looking at integers, not a range. So 19 different integers work. 61 through to 79. Right? The key point here, is if you have 2 points x and y on the number line, the distance between the 2 points is modulus of x minus y, which is nothing but modulus of y minus x. Both are same. The number of distinct pairs of integers m comma n satisfying this inequality. Wonderful, wonderful question. I really struggled with this one. So first thing to know is mod a less than mod b is same as saying a square less than b square. One implies the other. That's the first step to do. That means we can say 1 plus mn the whole square is less than m plus n the whole square, or 1 square plus m square n square plus 2mn is less than m square plus n square plus 2mn. Nice, so far so good. This 2mn gets knocked off on both sides. 1 plus m square n square minus m square minus n square is less than 0, or 1 minus n square minus m square plus m square n square is less than 0. 1 minus n square minus m square times 1 minus n square is less than 0, or quite beautifully 1 minus m square into 1 minus n square is less than 0. Nice. We're looking at distinct pair of integers. Product of two numbers is less than 0. Either this is negative, this is positive, or the other way around. Right? So either this is negative and this is positive, or this is positive and this is negative. The beauty of this is 1 minus m square is negative. That is reasonable. Lots of numbers. 1 minus n square is positive. 1 square is 1. N can't be 1. It will become 0. 2, 3, 4, 5, it won't work. Only possibility where 1 minus n square is positive is when n equal to 0. Only possibility where 1 minus m square is negative is when m is 0. So m equal to 0, n greater than 1 works. If m or n were 1, this one work will become 0. If m is 0, n greater than 1 works. Or n equals 0, m greater than 1 works. Nothing else is possible. If m and n are both more than 1, both will become negative, product will become positive. If either of them is 1, product will go to 0. That doesn't work. So one of them should be 0, other one should be greater than 1. So m0, n greater than 1, or n0, m greater than 1. That's a possibility. Now let's come back to this question. It's not n greater than 1. This is mod n greater than 1, mod m greater than 1. Because we're talking about n square. So plus 1 works and minus 1 work. Plus 2 works and minus 2 will work. Plus and minus 1 will not work. Plus 2 and minus 2 will work. Modulus of m plus n less than 5. This is an interesting thing. So let's attack that. Modulus of m plus n less than 5. If m is 0, mod n less than 5. When m is 0, mod n less than 5, n has to be greater than 1, be 2, 3, 4. N could be plus or minus 2, plus or minus 3, plus or minus 4. Exact opposite. If you put n equal to 0, we have mod m less than 5. We know mod m has to be more than 1. M could be plus or minus 2, plus or minus 3, plus or minus 4. So 0, 2, 0, minus 2, 0, 3, 0, minus 3, 0, 4, 0, minus 4. 6 possibilities plus 6, 12 possibilities. Super tough question. Really tough question. So it's kind of question which says, okay, I'm not touching this. We square this, then we get somewhere. And still there's a couple of steps to go. And wonderfully tough question. X square minus 7x plus 11 whole part x square minus 13x plus 42 is 1. Sounds like an incredibly tough question. But think about this. Any number par 0 is 11. So this could go to 0. And if you have a number 1.6 over anything apart from 0, it cannot be 1, because it's 1.6 per positive number, it will keep going higher and higher. Negative number will keep going less than 1. It can be equal to 1 only if it were 0, or the only time a non-zero power can give us 1
is 1 power something is 1. It's very simple. So x square minus 13x plus 42 equal to 0, or x square minus 7x plus 11 equal to 1. Solve these two, you're good to go. X minus 6 into x minus 7 is 0, 6 or 7. We need to substitute that to verify, but in both cases it's going to be some integer. We can even say it will be a positive integer. So 36 minus 42 plus 11, yeah, positive, nothing to worry. Substituting works. Or here we have x square minus 7x plus 10 equal to 0. X minus 2 into x minus 5 equal to 0. X is 2 or 5. You put 2 or 5, you put 2 square minus 26 plus 42, again nice positive integer, nothing to worry. You put 5, also will get a positive integer, nothing to worry. 2, 5, 6, 7, all of these work. 4 values. Hang on. There's one thing we have missed completely. We can even get 1 as minus 1 per an even number will give us 1. We'll have to verify that. How do you verify that? X square minus 7x plus 11 equals minus 1. X square minus 7x plus 12 equal to 0. X minus 3 into x minus 4 is 0. X could be 3 or 4. Minus 3 power, if you put x is 3, minus 1 power some number, could be 1 if that power is even. So put x is 3, 9 minus 39 plus 42. 9 minus 39 is minus 30 plus 42. This is 12. So x equal to 3 works. Put x equal to 4. That will definitely work. 16 minus 13 into 4, 52 plus 42. 16 minus 10, this is 6. That's also an even number. We get minus 1 per 6. So 3, 4 could work as well. So 2 and 5 could work. 6 and 7 could work. 3 and 4 could work. Or there are 6 possible values. I missed this one and I got 4 because I completely forgot the minus 1 power 4 thing. So beautiful question. You'll have to worry about this going to 0, this going to plus 1, this going to minus 1 in the time when this is an even number. The number of real valued solutions to the equation 2 power x plus 2 power minus x is 2 minus x minus 2 whole square. Beautiful question. You think about this. 2 power x and 2 power minus x are both positive. Fine. The minimum value this can take, this is of the form y plus 1 by y. The minimum value it can take is greater than or equal to 2. If it were negative, it will be less than or equal to minus 2. If it is positive, it is greater than or equal to 2. So this side is greater than or equal to 2. This side, this is greater than or equal to 0. Or this part is less than or equal to 2. From 2, you're subtracting a non-negative number. So maximum value the expression can be is 2. We're done. This has to be greater than or equal to 2. That has to be less than or equal to 2. The only possibility is if both are equal to 2. Be equal to 2 when x is 0. Put x equal to 0. 2 power 0 plus 2 power minus 0. This is 2. But if you put x equal to 2 here, we get 2 minus, x equal to 0 here. 2 minus 2 square. 2 minus 4 equal to minus 2. It doesn't work. This will go to 0 when x is 2. At that time, it is not 0. So there is no case where this is equal to 2 and this is equal to 2, or we'll have 0 real valued solutions to this. How many integers in the set 100, 101, 102 all the way to 999 have at least one digit repeated? The classic kind of question where you're asked for A. Finding A complement makes life easy. There are 900 numbers in this set that we should know. Now we want to find the number of numbers where no 2 digits are same, where nothing is repeated. A can go from 1 to 9, 9 possibilities. B can go from 0 to 9 except A, 9 possibilities. C can go from 0 to 9 except A and B, 8 possibilities. 9 into 9 into 8, 81 into 8, 648. There are 900 numbers totally, of which 648 have no 2 digits the same. They have distinct digits. The remaining 252 is the answer we are looking for. Have at least one digit repeated. So we're counting numbers like 252, 116, 444. All of them.